In this video, we demonstrate the general method for dealing with repeated roots. We've looked at second-order equations and found that if the characteristic equation has a single repeated root r, then e to the rt and t e to the rt are linearly independent solutions. We'll see that this generalizes to repeated roots of higher multiplicity, although the proof will require some work. This video is probably going to be a little long, but there's no obvious way to break it into shorter videos, so try to bear with it. Suppose we have a differential equation, a sub n, the nth derivative of y, a sub n minus 1, yn minus 1, to a sub 1 y prime plus a sub 0 y equals 0. We can rewrite this as a sub n d to the n plus a sub n minus 1 d to the n minus 1 to a sub 1 d plus a sub 0 applied to y equals 0. Now, the characteristic equation is a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub 1 x plus a sub 0 equals 0. Suppose this characteristic equation has a repeated root r of multiplicity k. Now, the fundamental theorem of algebra says that any polynomial can be completely factored over the complex plane. So we can rewrite this as a sub n times x minus r sub 1 times x minus r sub 2 to x minus r sub m times x minus r to the power of k equals 0. We get this term from the assumption that R has multiplicity k. So from this we have roots R1, R2, Rm, R. Each root gives us a linearly independent solution for the differential equation. But because of this root, we don't have a full set of n solutions. Goal: use the repeated root R to get k linearly independent solutions. So, for example, suppose the characteristic polynomial of a fourth order differential equation is 2 times x minus 2 times x plus 1 times x minus 1 squared. We need 4 linearly independent solutions. This gives us e to the 2t, and this gives us e to the negative t. But we need 2 additional solutions, and those both need to come from this root 1. So, we rewrote this differential equation in terms of the differential operator. Now we are going to factor this. It factors as a sub n times d minus r1 times d minus r2 to d minus rm d minus r to the power of k. That operator applied to y equals 0. We know this from the last video, where we saw that this multiplication, which is really composition, is done in the same way as standard polynomial multiplication. Well then, if this polynomial and this polynomial, so called, have the same coefficients, they factor in the same way. So this is not a characteristic polynomial. It is literally the differential equation rewritten using different notation. And we're now going to use this term to get k linearly independent solutions to the differential equation. Now, composition is associative. Remember that this multiplication is really a composition of operators, although it is acting like normal multiplication in many ways. So by associativity, we can rewrite these parentheses. One way for this equation to be true would be if this d minus r to the k applied to y equaled 0. If this is the 0 function, then when we apply all of this, we'll get the derivative of the 0 function, and the second derivative of the 0 function, and constants times the various derivatives of the 0 function, all of which will still be 0. So, new goal. Solve d minus r to the power of k applied to y equals 0. In the second order case, we tried using functions of the form u e to the rt. We found that works if and only if the second derivative of u equals 0. So let's try this again. What is d minus r to the power of k applied to u e to the rt? Let's look at, for example, k equals 3. So we've got d minus r, d minus r, d minus r, u e to the rt. We'll use associativity and look at this, d minus r u e to the rt by itself. Well, the derivative of this requires the product rule. U prime e to the RT plus UR e to the RT. This negative R times U e to the RT cancels with this U R e to the RT. So we find that D minus R U e to the RT is U squared, the derivative of U e to the RT. So applying D minus R to U e to the RT simply takes the derivative of this function. So D minus R D minus R D minus R U e to the RT is D minus R D minus R U prime e to the RT is D minus R U double prime e to the RT is the third derivative of U times e to the RT. Leaving this example and going back to the general case, D minus R to the power of K U e to the RT is the case derivative of U times e to the RT. And we want this to be 0. Well, e to the RT is positive. We can divide both sides of this equality by e to the RT. I mean, I say positive. What really matters is that it isn't 0. And doing that division gives you the case derivative of U equal to 0. And this we can solve. Any polynomial of degree less than k will work In particular, we get the following linearly independent solutions. E to the RT, T, E to the RT, T squared, E to the RT, T cubed, E to the RT, T to the K minus 1, E to the RT. Remember that K was the multiplicity of the repeated root R. We've seen in this video that if the characteristic polynomial has a repeated root of multiplicity k, we can get k linearly independent solutions from it. In the next video, we'll wrap up this material with an example.